Good morning, Sanjay.
Good morning, sir.
Yeah, then I will start. We will start right now.
Sure.
Good morning, everyone. Wishing you and your family a good health. I, Dr. Avinash Kumar, warmly welcome to our today's speaker, Dr. Sanjay Negi, as well as all the participants of webinar series, Indian Polar and Ocean Mission, which is being hosted by National Center for Polar and Ocean Research, an autonomous body, Ministry of Earth Sciences, to celebrate the India's 75th years of independence. Today we are having the sixth talk of this webinar series, and today the talk on the exploring the largest geoid low on Earth through the deep seismological observation. So before we start, I would like to give a brief introduction about today's speakers, Dr. Sanjay Negi. He is a project scientist at National Center for Polar and Ocean Research, and he has been associated with Indian Ocean Geoid Law program with the aim to understand the origin of the lowest geoid on the Earth. He has completed his master degree from IIT Kharagpur, and he has continued his research under the National Research Fellowship Program at Wadia Institute of Himalayan Geology, and was awarded this PhD degree from IIT Roorkee. His recent endeavor in designing the innovative methods and techniques to deal the noisy seismic datasets from the ocean bottom seismogram and to image the lithospheric and mantle structure beneath the Indian Ocean. Dr. Negi has published many research papers in peer-reviewed journals, and he has showcased his research in the several national and international scientific conferences. With this brief introduction, I will request Dr. Sanjay Negi to take over this webinar series, and I will request all the participants, if they have any remarks and query, they can write there in a comment box. Dr. Sanjay.
Thank you, sir. So I'll be sharing my screen. Is it visible?
Please first share, then it's not yet come. Yeah, it is coming now.
So is it visible now? Clear?
Yeah, it's visible.
So my today's topic of discussion is exploring the largest geoid low on Earth through deep seismological observations. So in the first section, so this particular slide basically explains the geoid low anomalies on the Earth's surface, and the most striking feature of geoid low anomaly is over the Indian Ocean geoid low region. So that's how I'll be discussing about this low geoid anomaly. So the topic, which I'll be the outline of my talk will be on. So just a minute. Yeah. So the topic, the main outline of my study is what is exactly the geoid. I'll be explaining the geoid and its significance. I'll be discussing about the Indian Geoid Law program at NCPOR, and I'll be switching on to the geoid anomalies and its link to the subsurface dynamics, and what could IOGL experiment contribute to the global studies, and finally the future of the ocean modern seismological studies in India. So I'll start with the historical perspective of what exactly how the geoid is imagined and how the shape of the Earth came into being. So starting with the spherical era, the Earth was initially considered to be as a sphere. So it all started in the 6th century BCE when Pythagoras, from his philosophical point of view, assumed Earth to be spherical. These observations came from the observed sphere shape of moon and sun. So that's how the spherical Earth was assumed to be as a sphere. Similarly, certain scientific attempts were made to estimate the size of the Earth, And these were the quantitative evaluations with the same conclusions. But further, Eratosthenes in 3rd century was the first person to actually estimate the mathematical shape of the Earth. And he estimated the shape using the arc length measurement. And that's how the spherical era ended with the Picard, who estimated the shape of the Earth on the basis of the triangulation methods. But further, with the improvement on the theoretical aspect, Isaac Newton started started the derivation of the Earth shape as an ellipsoid, and certain French expedition also happened, which proved Earth as an ellipsoid. So this was a brief overview of the historical perspective of the Earth's shape. So what exactly is the shape of the Earth? So by this study, we were able to determine that Earth appears to be as a spheroid of the ellipsoid, which is the quadratic surface obtained by rotating an ellipse about one of its principal axes. So there are two axes which from which one is defined as semi-major axis and semi-minor axis, and it defines the shape of the Earth. And geodesy is the scientific studies to determine the precise shape of the Earth. Here, when we look into the geodesy, it usually uses the gravity to define the shape of the geoid, and geophysics eventually uses the gravity variations to learn about the density variation within the interior of the Earth. So, moving to the next slide, what exactly is the geoid anomaly? So, the geoid basically is the observed gravitational equipotential surface that defines the sea level. Now, if you look into the reference geoid model, which was assumed to be as the ellipsoid or the spheroid or oblate spheroid we consider, this is termed to be as a reference geoid, which is a theoretical estimation of the equipotential surface of a rotating symmetrical spheroid Earth model. So the difference between the geoid surface, which is an observed gravitational equipotential surface, and the reference geoid, the difference between these two gives you the estimates of the geoid height, and that's how we define the geoid height. So there's a brief relation which is shown over here with the topographic height, the relation between the topographic height, the ellipsoid height, and the geoid height. So how we define it? The geoid height is basically the elevation from the ellipsoid, and when we estimate the topographic height, which actually is considered to be as elevation, so it is a difference between the ellipsoid height and the geoid height. Coming to the local geoid anomalies which we observe on Earth, by this cartoon model, we can see that the oceans here are replaced by a topographic feature, and when this topography exists, in that case, the geoid will, of course, it will be rising because of the density contrast between the ocean water and the mass introduced. So, but there are some local variations in the geoid height, and it is because of the low density masses or the high density masses lying within the Earth's surface. So that's how you can see over here that here we see that there is a low geoid which happens due to which occurs due to the low density material, whereas the geoid undulation will go positive because of the high density mass present within the subsurface. So that's how the origin of the potato model. So the Earth finally was considered to be as a potato model because of these undulations of the geoid. If you see another model, these are the local variations which we observe. These are the short wavelength variations which we see because of which the undulation can happen. And the other long wavelength undulations which can happen because of some of the features which underlie beneath the Earth's surface within the mantle. Now, as we know about the plate tectonic theory, in the plate tectonic theory, the ocean crust along the subduction zone subducts, and because of the higher density material, these could produce the positive geoid anomaly. And these, due to the large scale length of these slabs, this could produce the long wavelength anomalies, such as in the case of these geoid highs. Whereas if you see some of the plume structures, when it arrives or upwells in the upper mantle, because of the low density of these plumes, these can produce the geoid lows, as you can see in the area of Indian Ocean, over the Indian Ocean, which is termed to be as an Indian Ocean geoid low. So all these different geodetic reference surfaces are um, uh, for different are used for different purposes. And for example, the ellipsoid is used for locating the position of an object on the Earth's surface. Similarly, the geoid is basically used for defining the elevation, and this is how the geodetic reference surfaces are used for examining the Earth. Now, coming to the next, how we actually estimate uh, the geoid or the gravity variations on the Earth. So gravity recovery and climate experiment. This was the experiment which happened between the joint partnership of USA and Germany, and this actually initiated in 2002, and this mission was to accurately map the variations in the Earth's gravity field. So what exactly it does? In this, there are two twin satellites which are placed at a distance of 220 kilometers and orbits around the Earth's surface at 460 kilometers height. So what happens, how it measures these gravity variations? As it approaches, the distance is varied. So the variation in the distance between these two satellites is uh, is actually estimating is directly interpreted to estimate the geoid gravity variations on the surface of the Earth. So these gravity variations can be the small scale anomalies or the large scale anomalies. So what exactly this particular mission has established? It measures the gravity variation in the zone of the Earth, and also it is very important to determine the change in the water concentration. So a lot of studies are also, so there are different interpretation for such kind of study. So what significance it carries? The significance of the gravity and the geoid maps is basically that it with time it reveals important details about the polar ice sheet changes. The sea level variations can be estimated by studying these maps. Ocean current variations can also be studied. So these different sectors can be covered by utilizing the GRACE data. And the important point over here is that the internal structure of Earth can be determined. Actually, the variations in the gravity are indications of the subsurface anomalies, density anomalies, and which can have impact on the surface topography as well. So one of the examples, this slide shows the example of the gravity variation, how it monitors the ice mass changes. So here is one of the a small video to show you the how it with time it all started in 2002. So the monitoring over the Greenland, it actually explains that how the variation in the ice mass loss is happening. So it overall estimated that 281 gigatons per year of the average ice mass loss has happened since 2002 and 2016. There is another effect which can be observed by utilizing such kind of gravity anomaly variations. That is, during one of the earthquake which occurred in the Sumatra region, that was 2004 earthquake in the Indian Ocean, due to which there was a gravitational changes occurred, and that was very small scale gravitational changes which occur. But the important point to note over here is that these variations are also recorded in such kind of a data. So the variation in the gravity is quite nicely recorded, and that's how these are the small changes, like the seasonal and the annual changes are recorded over here. The sudden effects are recorded over here. So if we talk about the long wavelength anomalies which is observed from this kind of geoid data, so we can see that on this map, The valleys, as I have already explained, that negative geoid anomaly of minus 106 meters uh, exist in the region of the Indian Ocean. So this low low uh, uh, low height anomaly, which is in the Indian Ocean, it also exists in the Ross Island. This has also been identified in Canadian region, in the Caribbean, and also in the western offshore of the North America. Similarly, we observe the positive geoid anomalies, which lies in the south of the southern Africa, in the Indian Ocean. Also, one of the major striking feature of the positive anomaly lies in the Iceland, and also on the Philippine subduction zone. So these are the striking features, and somehow it kind of explains about what exactly is happening beneath the subsurface. So why these are the striking features is it is because of very long wavelength geoid anomalies are relatively insensitive to contamination from the lithospheric heterogeneities. Lithospheric heterogeneity means the changes in the elevations, the topography. So such low velocity low wavelength geoid anomalies are basically mostly related are sensitive to the deep-seated density contrast in the mantle. So that's how we have to understand exactly what is happening in the subsurface. To investigate that, seismology is the branch in which we study the deeper structures of the earth. So this is a small slide to explain that if you have a certain set of seismograms which record the different signals which are released from the earthquakes which happens in one of the particular, either it is in subduction zones or any kind of tectonic features. So the waves which we record, these waves can be utilized to actually sample the subsurface features of the Earth's interior. So with this, I would like to explain the Indian Ocean Geoseismic experiment, and it was the initiation by NCPOR in which total 17 ocean bottom seismometers were deployed during 2018 and 2019. So these are the inverted triangles which shows the location of the ocean bottom seismograms in the Indian Ocean geological region. There are certain other seismograms I have shown. These are the Indian networks, and some of the temporary array has been shown over here. The data was not only taken for the 1 year, there was a redeployment happened and for the sufficient and qualitative seismological data in 2019 and 2020. So overall, like 2 years of data was collected for during this experiment. The sensors basically, it contains 3 components: seismometers and a hydrophone. And the digitizer, the dynamic range of the system is basically from 120 seconds to 100 samples per second. So it has a broad frequency range and can be utilized for various studies in the ocean sciences. The interstation distance has been kept approximately near to 100 kilometers. Why it is so? Because we have to investigate the deeper parts, so that's why the interstation distance are kept at a broader level. The instrumentation and deployment plan. So going into the seismic experiment in the ocean domain, it is very important to first decide the deployment plan, where to deploy, and what are the features which are going to be highlighted after the study. So this is how we initiated with the deployment plan, and these were the breakpoints which were decided, and finally we came up with a plan to deploy all the stations with the distance as 100 kilometer already explained. And next is how these instrumentation record and what kind of instruments are are taken into consideration. This is a obvious system, and the important feature of this is the pressure tube, which actually maintains the high pressures at a deeper level of 6,000 kilometers, so 6,000 meters. And here inside this, there is a seismometer, which is from Nanometrics, and this is placed inside this. And there's a hydrophone over here. So these are the four component system, 3 component inside the seismometer, and the 4th component is the hydrophone, which records the pressure waves in the oceans. All these radio beacons are used to identify the locations while it pop-ups in the recovery time. So this small video will explain the deployment and the recovery operation. This is how the recovery happens. And once we recover the OBS, it is placed on board, and all the servicing is done before another deployment. So in servicing, we remove the data, and once the data is removed, we further assemble the OBS unit. And once the assembly has been done, we check the status of the data, that how the seismic instrument is performing. And once that is done, we again go for the deployment. Before that, very important point to note is that what kind of quality of the data has been recovered. That is very important, essential during the redeployment period. So for understanding that, a very important thing to note over here is that how we locate the OBS once it has been released to the depths of the ocean. So once at the deployment location we release the OBS, it can float. It can float to any direction because of the ocean currents. So to estimate the location, we do the ranging, and the ranging actually estimates the distance between the OBS where it is placed on the ocean floor, and between the location where we are ranging it. So by this ranging method, it is a simple Pythagorean theorem by which we estimate the water depth, and the location is estimated by circling it around three different positions. So from three different positions, the ranging is done to identify the obvious location. Actually, this is the case where we are studying the deeper phenomena are being studied. But if someone wants to study the local phenomena, means local observations like local earthquakes, in that case, this triangulation and the ocean bottom seismometer location has to be very precise. For that, these ranging points should be increased more than 10, so that the precise location of this OBS can be find out. So this is one of the very important tasks during the OBS deployment. Now, actually, why I want to highlight this particular slide is because after the recovery, once the data is recovered, it is very important to first of all to recover all the OBSs. But sometime in misfortune happens, and because of which there is some of the OBS are not recovered. So in that case, I would like to highlight that in this experiment we recovered all the seismometers on board, and all the data was recovered. So I would like to highlight two important points which have been achieved during this program. It was kind of a multi-institutional participation happened in this program, and hands-on training was also provided during the OBS deployment and retrieval for the students which participated in this expedition. These were master students, research scholars, and scientists from different universities and institutions. So that was one of the things which was also provided. An outreach kind of a activity happened during this expedition. So what do we get once we retrieve the data? We the Earth actually vibrates all the time, and apart from that, in the subduction zones and various intracontinental regions, the earthquake happens. So all these earthquakes are recorded in the data. But due to the ocean seismic noises, these data are quite variable. The seismic noise disturbs the whole of the data. So here in the first plot, uh, all these earthquakes, total 449 earthquakes uh, have been recorded during the month of May to June 2019. In the next slide, I would like to explain what a four-component seismogram data looks like. In one of the station, OBS 8, this is the hydrophone data, which also shows the semi-diurnal ocean tidal currents, which are quite visible in the hydrophone data. There's a vertical component which we observe over here, and some of the spikes we can see it would be the signal or the noise. So this kind of data we observe, which actually is very noisy, as you can see. So in these challenges, we have to actually extract the earthquakes and continue the further studies. Uh, so also the horizontal components, if you see, you can see that there are certain this actually, these are also the tidal effects which can be observed in the horizontal components. This is one horizontal component which is considered to be just like this land data. One of the component could be north-south, but these are not actually aligned. So we have to further align these horizontal components into the right direction, north-south and east-west directions. So what are the challenges exactly when we see the data? There is a lot of seismic noises in the data set. And second is large data set archives has to be done. Archiving has to be done, and easy data access modules should be ready to actually study such large data set. So what could be the solution for such challenges and the priorities we have to make during studying these ocean bottom seismometer data? The solution is to develop some of the softwares, the soft tools for ocean geosciences. On the right side, there is one of the example. As I've already explained that there is a lot of noise which you will observe in the ocean bottom seismograms, and these noises basically would not let any user to identify the signals. Either it is the P waves or the S wave or any kind of waves. So in this situation, uh, uh, this seismic noise has to be reduced, for which we developed a module of noise reduction on the MATLAB platform. And basically what it does is, this is a data adaptive polarization filter in which the data is first inputted, inserted, and certain parameters, we can actually changing the different parameters of the adaptive polarization filter, we can actually extract the signals from these, as you can see in these three traces. So this is the raw data, and here you can see these are the filtered data, and these are the extracted signals from the noisy trace. So this is one of the example which, and here you can also see the spectral analysis on this final data is performed to see this how much spectrally we have enhanced the signals. The another thing is how to deal with the large data set from the ocean bottom seismometers. There are a lot of other soft tools which are already provided, but to actually deal with this kind of study, we need to have our own understanding of certain softwares, and for that we have also developed some earthquake waveform analysis tool to actually analyze the earthquakes which we have recorded in this system. So here you can see that there are a lot of filters provided in this of different range. So users can actually utilize these kind of these filters to see the signals. All the three traces can be visualized at different time. This is a vertical trace which is being shown over here. And if you see, also the latitude and longitudes means the location of these earthquakes are appearing on the screen. So these are some of the initial things which should be done in the and taken as a priority in ocean geosciences. The next, I'll now come to the next. One of the very important tasks, which is quite cumbersome during the onboard data quality assessment, because why it is important is because the quantitative analysis and qualitative analysis of the data is before the deployment. So if in case like statistics of the data availability, and so the site specific, actually when you deploy OBS seismometer at particular location, so the noises at a particular site can be very high. So these quantitative analysis and qualitative analysis actually helps you to take a decision at that particular time, that whether further redeployment has to be done or not. So these are some significant tasks which are required during the obvious deployment. So coming to the actual the study which we have undertaken, the seismological deep investigations, by utilizing the signals which we have acquired from this experiment. So this is one of the example of an earthquake. This is a moment magnitude of 8.2. This is a quite large earthquake. This is a great earthquake, and which occurred at a distance of 103, somewhere around like 10,000, 13,000 kilometers, and the azimuth, the direction is 108, and so we can observe the P waves over here, but overall what we see is it is not quite as visible if as compared to the large earthquake magnitude. Such kind of data should be expected by the users when you work with the ocean bottom seismometers. But the important point is that how we actually sample the Earth in seismology deep investigation by considering two different types of waves. The first one is the body wave. We all have studied all these things, but to just highlight that what exactly the P wave motion is, particle motion, it is along the direction of propagation. Similarly, the S wave is the transverse motion, and these body waves travels inside the Earth and samples the Earth within the Earth's surface, subsurface, and because of which we can investigate actually the deeper regions by studying these body waves. There is a surface wave analysis. So both of these waves were utilized in our analysis. So I'll be in the next slides. I'll be explaining how we have actually done utilize both the waves to study the Earth's subsurface. So the first point I would like to highlight the crustal effects on geoid. So one of the study was done on the basis of the active OBS experiment. So the active OBS actually explain is quite efficient to define the crustal structure, the shallow crustal structure, and it is considered that crustal structure and the moho depth has considerable influence on the observed geoid over a region. So this diagram has been already shown, but whenever there is a mass deficiency, so because of which the geoid low appears, whereas geoid positive appears when there is a mass surplus. So by studying this data, which is from the ocean bottom seismograph, the active ocean bottom seismograph, and studying the refracted waves, a conclusion was small model, the crustal model is prepared. What it exactly explains is that on the eastern, near to the Comoran Ridge, we have the mass deficit, because of which the crustal thickness is quite, the crust is quite thick near to the Comoran Ridge. As we go away in the eastern direction, away from the Comoran Ridge, we have the thinning of the crust. So it simply explains the thickening of the crust explains the mass deficit, because of which we can see the similar results which is observed in the uh, ocean geoid surface. So here we have the low geoid, and as we move away from this, the geoid increases, as the thickness also decreases. So the increase in the geoid and thicknesses, because here what happens is like the upper mantle is replaced by the crustal material which has a low density. So because of which there is a mass deficit, which is shown over here. So this is one of the crustal observations which we have made from the data. Another thing, before going uh, deep into the mental investigation, I would like to put forth few theories to explain the geoid law. Already people have worked and have there are two school of thoughts to explain the theory behind the geoid law. One is the subducted slab graveyard theory, and another one is the low density anomaly in the upper mid mantle. So, what exactly are these theories? I'll be explaining it through these diagrams. And this is a work which was done on the Pacific area, and by Pacific, and basically these are also the region where the low geoid anomaly exists. So as you can see that this is a geoid anomaly map over here, the low geoid in the Ross Island, and here you have on the Pacific side, northern Pacific, you have the low geoid. So the investigation, this is a tomographic map, and this tomographic map shows that in the geoid low region, there are two important striking features which has been observed. One is in the lower mantle, there are subducted slabs, and because of these subducted slabs, and at the same time, in the shallower upper mantle and the transition zone, in the upper mantle and the upper part of the lower mantle, there are strikingly low velocity anomalies which were observed. So because of which this theory came into existence, that the subducted slab graveyard along with the low velocity anomalies on the shallower part would give rise to the low geoids. And similar studies were performed to explain that this at the base of the Indian Ocean to actually define these subducted slab graveyard on the western Indian Ocean. So here, this is one of the study by Rao et al, and they have explained the anisotropic through the anisotropic study. They have tried to explain the D double dash layer at the depth of Indian Ocean. So this is how the slab subducted graveyard theory was propagated to explain these geoid lows. Another theory comes from the low density anomalies, which lies in the upper mid-mantle. So here, the main focus was to observe this geoid. So this is a geodynamic modeling, which this is a geoid, which was produced using one of the tomographic models, the gypsum, developed by Simmons in 2010. And this is the P-wave. This geoid anomaly is produced using the P-wave tomography. This is the shear wave tomography inversion results, geodynamic results, and these are the geoid variations which were produced after inverting the gypsum S model, and another model was also undertaken. So these three models quite well explain the long wavelength geoid anomalies in the Indian Ocean. So this is how these uh, two different sets of school of thoughts explain the geoid anomaly in this region. So overall, concluding theoretical model can be assumed that whenever there is a subducting slab in the upper mantle, what we can observe is a positive anomaly. As we can see the positive anomaly in the Philippine region, where I have shown that already that region is the Pacific plated subducting beneath the Philippines, and there is major subduction happening over there. So because of which there is a positive geoid anomaly, but it also counterparts because in the Iceland region there is no subduction happening, but still there is we have the positive anomaly. And if you see this subduction slab as we have seen in the previous slide, if it occurs, if it is introduced in the lower mantle, so it flips the direction of the geoid, and the geoid shows the negative effect. Similarly, if in the upper mantle, if there is a low velocity anomaly or plume-like anomaly, so in that case, the geoid is basically has the negative polarity, and vice versa if the lower mantle has a plume. So if you take out the two best possible model to explain the geoid, so in the upper mantle, if this low velocity anomaly lies, and in the lower mantle this uh, high subductant dense subductant slab uh, is existing, due to this negative geoid anomaly can be produced. So these were the concluding theoretical models from the recent studies. Now we investigated the surface wave and tried to sample the shallower upper mantle region, and in that we tried to use the Rayleigh waves because as it has the ellipsoidal motion, and it has the dispersive nature, because of which the higher frequency samples the shallower region, and the low frequency samples the deeper region. And by utilizing these Rayleigh waves, we have actually estimated the velocity, 1D velocity model beneath the Indian Ocean. So this is one of the model, the priori model which has come, and the surface wave. Yeah, the first diagram shows you the locations of the obvious stations, and all these stations we have estimated the group velocity as well as the phase velocity dispersion. And this is the example. You can see, observe here that from the ocean bottom seismometers we can actually go from like 15 seconds up to like 200 seconds of the data can be utilized to investigate. So we can have a very good idea of up to like 400 kilometers of depth by utilizing this data. So this is one of the model which we have estimated. And here a very striking feature which we observe in the upper mantle is the low velocity zone, which is quite broad. Usually such kind of low velocity anomalies are quite thin in beneath the oceans, but in this region we observe a very broad low velocity zone. So from the surface wave analysis in the shallow region, and another important thing is that here the lithosphere is uh, thin. It is up to like 55 kilometers. So this is the another observation which we made through surface wave dispersion. Next, for a deeper investigation, we also utilized receiver function method, and this method is basically samples the deeper part of the Earth. There are important discontinuities, as we know them as like 14-kilometer discontinuity and the 660-kilometer discontinuity, which marks the transition zone. So this actually this transition zone separates the upper mantle from the lower mantle. So whenever the earthquake strikes, so the energy when received at the receiver, when it passes through these boundaries, so it is splitted into the P wave is converted into S wave. So it, that's how, because the P wave is converted into S wave and the speed of the P wave is faster than the S wave, because of which it will be delayed. So that's how the receiver function works. So here we deconvolve the radial. This is one of the component. This is the horizontal component, which is rotated to the radial component, and this radial component is reconvolved from Z component to actually estimate the receiver function. And these receiver functions are stacked to actually sample these boundaries, which are very important to highlight the various anomalous features within the subsurface. So this is very important slide to understand what exactly happens at these 410 and 660 boundaries, and what exactly these 410 and 660 boundaries are. So 410 discontinuity is the discontinuity where the olivine changes to wet slate. So wet slate is basically the high pressure polymorph of olivine, and here at this boundary, and it shows a contrasting impedance contrast, quite high impedance contrast over here, because of which this anomaly is highlighted in the seismic investigation. Similarly, we have 660-kilometer discontinuity, and it also marks a very important change, the polymorph, which is the ringwoodite, and it converts to perovskite. So this marks the boundary of conversion of ringwoodite mineral to perovskite and magnesium-leucite. So these two boundaries, why it is important, we can understand it from the Clausius-Clapeyron relation. What exactly is the Clausius-Clapeyron relation? It characterizes a discontinuous phase transition between two phases of matter of a single constituent, and it varies with depth. So here, this is basically a positive Clapeyron slope, and here when olivine changes to its high pressure polymorph, and this condition, when there is a cold regime, if the mantle is colder than the ambient mantle, then it will shift upwards, as can be seen over here. So this is a major transition which happens where this 410 anomaly is basically elevated, and the similar will happen with the 660. It will be depressed. So here we will get a thicker transition when there is a cold anomaly which is introduced. Now, when I say cold anomaly regimes, what exactly it means? Uh, when we see this cross section over here, there is a subduction which is happening by this. It is explained in this. We can see this cartoon in which this particular zone defines the subducted slab. and this subduction actually shows the colder. Uh, it shows the colder regime. Why? Because the ambient mantle is much hotter than the oceanic plate. So when it is introduced inside the Earth, it represents the colder regime. So whenever there is a subduction, we will find the anomaly of 410 and 660, which shows the broader transition zone. And if we see the hot regime, in hot regime means the plume when the hot plume rises from the core mantle boundary, it kinds of halts over here and can when it crosses the buoyancy limit of this particular transition zones at this zone, it deflects in a different fashion. For the hot regime, you can see that as we move in the positive direction of this particular slope, we see that it is kind of depressed. So the depression happens over here. Why? I'll take a little bit of time to explain this because the main results are actually dependent upon this slide to get explained. So here I am trying to explain that whenever there is a mantle plume which is introduced in the system, which is hotter or extremely hot, so what kind of changes happens in this boundary? So whenever there is another Garnet dominant system appears, which actually shows the extremely hot regime, in that case the 410 kilometer and 660 kilometer will be depressed. So these are different changes which we observe. So moving to the next slide. So we considered these earthquakes to sample this 410 and 660 kilometer boundaries representing the transition zone boundary. And along this profile, we took three profiles. One is AA- section and BB- section. So important here is the AA- and BB- section, which samples the north-south profile of the Indian Ocean geoid low region. So we are going to go from the lower geoid anomalies to higher geoid anomalies towards the center of this lowest geoid anomaly in the Indian Ocean. So that's how we want to see the changes what are happening from when we start from the outer ridge of the anomaly towards the center of the anomaly. So in the next slide, I'd be showing you the result in which these are the receiver functions which are obtained at each stations, right, starting from the A to A- section. And here, when you observe these positive amplitude shows the 410 boundary, and when we correlate these along the profile, we see that there is a major depression in the 410 boundary. Again, if you observe the changes in 660 boundary, so we observed as we go towards the center, there is a major depression seen in this boundary, and overall it represents a depressed transition zone. So this was one of the observations which explains that it basically has a Garnet dominant system. The mantle is basically Garnet dominant system over here, and it is extremely hot. Uh, The another point is that when we overlay these receiver function results on top of the one of the tomographic model. So this tomographic model we have taken from French and Romanovic in 2015, and this tomographic model shows a low velocity anomaly in this region, which is quite prominent, and it has its base nearly around 1,000 kilometers and shows an upwelling effect, kind of mantle upwelling can be observed in this particular diagram. So these are the low velocity anomalies if we see from seismic perspective, whereas from the receiver function analysis, we can observe that these are the hot anomalies. So we can assume it as a plume, which has a mantle upwelling effect that can be seen, which is coming right starting from the lower mantle to the upper mantle. So this was one of the major contribution from the OBS data which we have estimated. The another very important point is the evidence of the recycled subducted slab. So this eclogite segregation, eclogite is one of the high pressure mineral, and this basically concentrate and shows the evidence in the receiver functions at 300 kilometers. So this 300-kilometer boundary, if highlighted, actually represents the eclogite segregation in that zone. and this is quite high density material. Although it is a high density material, but still it has it actually explains the evidence of a recycled subducted slab. So both both of these hot temperature anomaly and recycling of the subducted slab proves the previous supports the previous study, and the mental appealing of this can be inferred from this particular results which which we have estimated from the receiver function analysis. So these are two major striking things which we have estimated in the deeper part of this region, IOGL region. So if extremely hot mantle plume exists beneath IOGL, how is it still contained within the subsurface? That is one of the questions that can be addressed in future studies. So this is a question which I'll leave to the users as well. The next slide is the contribution of IOGL experiment to the global studies. So what kind of contribution this IOGL experiment can contribute to the global studies? As you can see, these two diagrams, it shows uh, uh, the seismological network of over the Asian part and the African part. And all these red dots basically shows the all these all these all okay, fine. All these red dots basically shows the seismic stations in the Asian part and the African part and the Indonesian region. So, but we see the huge lacuna in the Indian Ocean. Not only in the Indian Ocean, it can also be observed in the Pacific Ocean where the seismic distribution is not there. So major part of the global studies utilizes all these networks to study and understand the subsurface features. But due to the lack of the data, we actually extrapolate the models to explain the anomalies. So this is a closer view for that how many stations are overall, an average estimation of the seismic stations which are distributed around the Indian Ocean geoidal region. So this, if this array, such kind of array is there, just like an IOGL experiment, then it can contribute to one of the major study. Uh, these two slides are two different models of the same region. This is a tomography model, the shear wave velocity model, and you can see at the similar depth, approximately near to this and nearly similar depth, you can see that these low velocity anomalies have different shapes. So the differences between the tomography model can be resolved if we have the well distribution of these such kind of experiment in the Indian Oceans or in the Pacific Ocean as well. So one of the major contribution of this experiment can be utilized in the global studies, and which can actually give the true models of the subsurface features within the Earth. The second is the future of
Excuse
ocean
me,
bottom.
Dr. Sanjay.
Yes,
Yeah, it is the time will be up, so you may try to bind up first.
sure, sir. Sure. This is the last uh, future of ocean bottom seismological studies in India. So what could be the future of such kind of ocean bottom seismological studies? First would be the monitoring the local seismicity in the Indian Ocean and determining the subsurface active fracture zones in such regions where there is no sampling of the subsurface feature. So the local seismicity can be monitored by such kind of ocean bottom seismological studies. Another is very important uh, thing we can highlight is the submarine volcano study can also be undertaken as by recently done by one of the NIO group research group. The submarine volcanoes can also be monitored and the related hazards in the oceans can be monitored by this. So this is one of the example which shows the local earthquakes in this region, and quite a lot in single day you can observe a lot of local seismicity. In the previous, this particular diagram does not show any kind of local activities in the region because these are the global stations which have contributed to the seismic investigations, whereas the local network shows a lot of earthquakes. So this local earthquake seismicity can also be monitored in future. and interplate deformation, of course, because it is, and there's a lot of debates happening over the diffuse interplate deformation in Indian Ocean, and quite large earthquakes are happening over this region. So why actually these large earthquakes happens within the intercontinental regime is a big question to be addressed, and such kind of investigations can help us to actually investigate these diffused interplate deformation in the Indian Ocean. So with this, I would like to thank. Uh, uh, I would like to thank you.
Thank you so much, Dr. Sanjay, for a very detailed and informative talk on the geoid law of the Earth. I must say the Earth interior structure is still a mystery to be solved, as this blue planet looks fair in the shape, but it has its own share of deformities, as we know that. So I think with this, I can see there is no questions. One query has been asked that is there any role of geoid law in sea level changes?
Yes, actually, role of geoid actually because of the sea level changes, the geoid law variations, the geoid surface actually varies. So it has the reverse effect. That means if the sea level will be changing, in that case, the geoid.
Okay. So I think I can see there is no other any queries. I think your talk was very detailed and informative. People may relook your talk, and if any queries, they may contact you directly, or maybe they can write their questions in the YouTube. It will be available throughout the year. So with this, I think today was the last lecture of webinar series, and I take an opportunity to extend my hearty gratitude to Ministry of Earth Sciences for encouraging to organize this informative web series on this occasion of India's 75th years of independence. This program was actually not possible without the immense support of our director, Dr. I'm thankful to us for giving their valuable time and sharing their knowledge with us. I extend my warm thank you to our group director, Dr. Rahul Mohan, his International Cooperation and Outreach Division, for his motivation and support. And I also thank to our team, Dr. Swati Nagar and Ms. Juhi Yadav, for planning and coordinating this event. This was completely a virtual learning program, and I really thank to NCPOR IT division, Mr. Samiji and Nixon for making this event successful. No event can be happen without the provision of a vast network of the people. And so behalf of NCPOR, extend all the participants who have joined this virtual platform of this webinar series. We will be very soon, we are going to organize start the next web series, which will be comprising of the very interesting talks from the national and international researchers. So I think for that, very soon we will be announcing that next talk series that right now we are working on that. So with this, I think I wish you for your good health and safety and have a great day. Thank you so much and namaskar.
Thanks.